Welcome back to the Deep Dive. We're here again to take a really big subject, pull together the key sources, and basically give you that shortcut to being genuinely well-informed. Today, we're doing an immersive exploration of the Atlantic Ocean. And we're not just talking about a big patch of water on the map. This is about a dynamic engine that, well, it drives global climate, it shapes trade, and it even holds secrets about our planet's geological future. When you think about the Atlantic, the first thing that hits you is just the scale, right? Our sources hammer this home. It's the second largest oceanic division on Earth. We're talking roughly 85 million square kilometers.
Yeah, that's a staggering 17% of the entire globe's surface. It's immense.
Exactly.
Yeah.
But its influence, it runs much deeper than just size. Historically, it's been this defining boundary,
Yeah.
famously separating the Old World, Afro-Eurasia, from the New World of the Americas.
That's right. And this very distinct, elongated, sort of S-shaped basin, it's unique in how its own history really mirrors human history. So our mission for this deep dive, it's pretty ambitious. We're digging into sources that span millennia. We're starting way back with ancient Greek mythology.
Wow, okay.
And bringing it all the way up to complex modern climate models. We really want to show you the mechanisms behind it all, the geology, the hydrology, the human consequences, everything that defines this ocean, how it came to be, and maybe surprisingly, why the geological evidence suggests it's actually very slowly preparing for its eventual closure.
Closure. Okay, that's a hook. Let's start with the name itself then. Atlantic. It feels so fundamental, but where does it actually come from?
Well, the origins are surprisingly specific. The toponymy, the study of place names, traces it back to the mid-6th century BC. Specifically, it seems, through the work of a poet named Stesichorus. The original term, Atlantikoi Pelagiae, literally meant the Sea of Atlas.
Atlas, the titan holding up the heavens.
Exactly that one. It plugs right into the mythological world. For those early Greek thinkers, especially around the Mediterranean, the real ocean, the one surrounding all known land, they generally called that Oceanus.
Right, like a big river around the world.
Precisely. They pictured it as this gigantic river flowing around the known world. So the term Atlantic wasn't initially for this massive ocean we know today.
So it was more localized.
Oh, very much so.
Yeah.
At first, Atlantic strictly referred only to the waters right off the Atlas Mountains in Morocco, near the Strait of Gibraltar.
Huh.
It was only as exploration pushed further west, centuries later, that the name gradually stretched to cover the entire basin.
And that took a surprisingly long time to standardize. Our sources point out that even into the mid-1800s, the southern part, what we call the South Atlantic now, was sometimes still called the Ethiopian Ocean.
Right, derived from ancient Ethiopia. It really highlights how slow that process of global geographic naming and agreement actually was.
It does. And speaking of names, there's that colloquial one, the pond.
Yes, the pond. My favorite.
Used by British and American speakers for the North Atlantic. It's such a classic bit of meiosis, that ironic understatement, isn't it, given its actual size?
It really is. And what's fascinating is that it's not some modern slang. The sources show it in print dating back to at least 1640.
1640, wow.
Yeah, centuries of travelers trying to casually downplay this monumental, often dangerous voyage across thousands of kilometers of ocean.
It's hard to keep up that understatement when you look at the sheer physical facts, though. As we said, it's defined by that long S shape, and the equator splits it neatly into North and South Atlantic.
But the volume, the numbers are just humbling. The total amount of water is over 310 million cubic kilometers.
Mind-boggling.
It is. Now, interestingly, despite that huge surface area, its average depth is 3,646 meters. That's actually a bit shallower than the global ocean average, which is around 3,700 meters.
But the range is huge, you mentioned, from shallow areas to extreme depths.
Absolutely. The extremes are quite breathtaking. While 3,646 meters is the average, the deepest point anywhere in the Atlantic is the Milwaukee Deep.
Where's that located?
It's within the Puerto Rico Trench, and it plunges down to 8,376 meters.
Okay, perspective check. How deep is that, really?
Put it this way. You could stack nearly 3 Empire State Buildings end to end in that trench, and the top one would still be underwater.
That is incredibly deep.
It is. And the Atlantic's edge isn't smooth either. Its coastline is incredibly indented, featuring dozens of major marginal seas, The Baltic Sea, the Caribbean, the Gulf of Mexico, the Mediterranean.
All connected but distinct.
Exactly.
Hmm.
And even if you take out the area covered by all those marginal seas, the main Atlantic Ocean basin itself is still nearly 82 million square kilometers. It shows just how dominant the main basin really is.
And this geography, the shape, and the connected seas, it must directly influence climate, right?
Yeah, definitely. The South Atlantic, especially around the tropical countries bordering it, tends to have pretty consistently warm temperatures all year round. The North Atlantic, though, is a different story. It shows really dramatic seasonal changes. The way the currents move and the sheer volume of water interacting with those huge land masses, North America and Eurasia, means it experiences seasons of both very low and very high temperatures. It's much more variable.
Okay, let's dive deeper then, literally, into the geology. If we could somehow drain all that water, what's the dominant feature we'd see?
Without a doubt, it would be the Mid-Atlantic Ridge, the MAR. It's the literal spine running down almost the entire length of the ocean.
A spine, like a mountain range.
Exactly. It's a massive submarine mountain range. It runs longitudinally north to south for nearly the whole ocean. We're talking from 87 degrees north, way up in the Arctic,
Wow.
all the way down near the subantarctic at 54 degrees south, close to Bouvet Island. It is by far the longest mountain range on our planet, over 16,000 kilometers long.
And it's not just sitting there. It shapes the whole floor.
Absolutely. It rises dramatically, usually about 2 to 3 kilometers higher than the surrounding deep ocean floor, the abyssal plain. But the crucial part is the rift valley right down its center. That's the divergent boundary. That's where Earth's major tectonic plates are actively pulling apart.
So in the North Atlantic, that's the North American and Eurasian plates moving away from each other.
Correct. And in the South Atlantic, it's the South American and African plates separating.
And this separation is what's actually creating the Atlantic.
Precisely, inch by inch, day by day. As those plates pull apart, magma from the Earth's mantle rises up into the gap, cools, and solidifies, forming new basaltic ocean crust.
So the ocean floor is constantly regenerating along that ridge.
Constantly. And where this ridge actually breaks through the ocean surface, that's where we see active volcanic islands. Iceland is the prime example. It sits directly on top of the spreading center.
Hence the volcanoes, like Eyjafjallajökull, that caused all that disruption.
Exactly. That's the ridge manifesting itself above sea level.
We sort of take plate tectonics for granted now, but mapping this ridge was fundamental to proving the theory, wasn't it? What's the story there?
It was absolutely key. The very first hints came, almost accidentally, during the famous HMS Challenger expedition back in the 1870s.
How did they find it?
They were taking deep sea soundings, measuring depth, and they kept noticing this elevated ridge, a significant rise on the seabed. They knew something substantial was down there, but they couldn't map its full extent with the technology they had.
So who actually put the whole picture together?
That really fell to the German meteor expedition in the 1920s. They had a crucial advantage. New echo-sounding equipment.
The sonar, basically.
Essentially, yes.
Yeah.
It allowed them to map the seafloor bathymetry, the underwater landscape, systematically and much more accurately. They were the ones who confirmed the full continuous S-shape of the ridge system.
But just knowing it was there didn't immediately explain why it was there.
Not fully. The true significance, the connection to seafloor spreading, wasn't really locked down until the 1950s. Later explorations, mapping the magnetic stripes on either side of the ridge and examining the Rift Valley itself, provided the undeniable evidence for seafloor spreading.
And that became the cornerstone of modern plate tectonic theory.
It really did. The MAR was the proof.
You mentioned the ridge acts as a barrier.
Yeah.
How does this huge underwater mountain range affect the movement of the deepest ocean waters?
It functions almost like a massive wall or a continental divide, but for the deep ocean. The ridge is generally impermeable to the densest, coldest bottom water that flows southwards along the ocean floor.
So it keeps the deep water on the west side separate from the deep water on the east side.
Largely, yes. The deep currents near the Americas are mostly isolated from those near Africa and Europe. However, there are crucial gaps.
Ah, exceptions.
Yes. The ridge is interrupted in places by massive transform faults. These are like huge horizontal cracks or breaks in the crust that cut across the ridge.
And water can pass through those.
Exactly. The two most significant breaks are the Romanche Trench, which is near the equator, and the Gibbs Fracture Zone, up around 53 degrees north. These faults create deep water passages. They're essentially the only places where the coldest bottom currents can actually flow from one side of the Atlantic basin to the other.
Fascinating. Now, looking way back, the Atlantic itself is relatively young geologically, right? Born from the breakup of the supercontinent Pangaea. How did that initial split happen?
The very first phase, what we call the Central Atlantic Opening, kicked off roughly 270 million years ago during the late Triassic and early Jurassic periods. And this wasn't a quiet process. It coincided with one of the most violent volcanic episodes in Earth's history, the massive eruption of the Central Atlantic Magmatic Province, or CAMP.
Camp sounds pretty dramatic. What exactly was that?
It was truly apocalyptic. CAMP is one of the largest known large igneous provinces, or LIPs. We're talking about an estimated 4.5 million square kilometers covered in lava flows.
4.5 million. Where was this?
It stretched across areas that are now North and South America, Africa, and Iberia, back when they were all joined together in Pangaea. This enormous, sudden outpouring of basalt lava and associated gases like CO2 and sulfur dioxide. It's directly linked by geologists to the severe climate shock that triggered the Triassic-Jurassic extinction event.
Wow. So the birth of the Atlantic is tied to a mass extinction.
Directly. This event wiped out a huge percentage of the planet's terrestrial and marine life. It essentially cleared the ecological slate, paving the way for the age of dinosaurs to really take hold. The geological birth of this ocean was born from global catastrophe.
That really drives home the scale and violence of these planetary processes. But the Atlantic didn't just pop open all at once, did it? You mentioned stages.
No, absolutely not. It opened more like a zipper, starting in the center and then progressing north and south. The North Atlantic developed later. Spreading there really got going, opening the Labrador Sea between Canada and Greenland around 61 million years ago.
And Iceland, you mentioned it earlier.
Iceland's a special case. Its formation, starting around 62 million years ago, isn't just due to the mid-Atlantic ridge itself. It's thought to be powered by an underlying, unusually intense mantle plume.
A hot spot.
Exactly. A particularly concentrated upwelling of superhot rock from deep within the Earth. This plume caused tremendous crustal uplift, not just in Iceland, but across surrounding regions too, like East Greenland and parts of Scotland.
You can still see the geological effects today.
Okay, so that's the North. What about the South Atlantic, the split between South America and Africa? That happened mainly in the early Cretaceous period. When West Gondwana, that southern part of Pangaea, broke apart, that split was also marked by intense volcanic activity, though slightly later than Campi.
Another LIP.
Yep. This created the Paraná-Etendeka large igneous province. Again, huge volumes of basalt flooded across areas of modern-day Brazil, Paraguay, Uruguay, and also parts of Namibia and Angola in Africa.
And the fit between those coastlines is famously perfect.
It's the classic textbook example supporting continental drift, that almost perfect jigsaw puzzle fit. Still spectacular evidence.
Now, moving closer to the present, there's a geological event that had huge consequences for the modern Atlantic and global climate, the formation of the Isthmus of Panama.
Ah, yes, the closing of the Central American Seaway. This is absolutely crucial, especially if you're interested in climate dynamics. For much of Earth's recent geological history, there was a gap there, allowing water to flow freely between the Pacific and the Atlantic.
But then Central America formed a land bridge.
Exactly. The Isthmus of Panama finally closed that gap only about 2.8 million years ago. Geologically, that's quite recent. And this seemingly small connection of land had profound, truly global consequences.
You referred to it in the outline as the Great American Schism. What did it do to the oceans?
Well, before the closure, the currents between the two oceans were more mixed, probably weaker overall. When the isthmus formed, it completely separated the two ocean basins at the surface. This forced the Atlantic equatorial current, which carries warm and very salty water, to turn northward instead of leaking into the Pacific.
So it piled up warm, salty water in the Atlantic.
Essentially, yes. It dramatically increased the salinity and temperature of the North Atlantic surface waters. This major change is thought to have been the driving force behind the development, or at least the intensification, of the strong heat-carrying current system we see today, especially the Gulf Stream.
So it didn't just allow the Great American Interchange where land animals migrated between continents.
Right, that was the terrestrial consequence.
It fundamentally rewired the planet's ocean circulation system.
Precisely. It intensified the whole Atlantic circulation, pushing much more heat further north than before. And ironically, some climate scientists believe this increased heat and moisture transport to high latitudes might have actually helped trigger the major northern hemisphere ice ages.
Wow, creating warmer currents helped start ice ages. That's counterintuitive.
It is, but the idea is that more moisture in the north led to more snowfall, which built up the ice sheets. It's a fantastic example of how one single geological event can ripple outwards, affecting global climate and biology in complex ways.
Okay, that focus on salinity and temperature is a perfect segue into the Atlantic's water characteristics. You mentioned it's salty. How salty are we talking?
On average, the Atlantic holds the title for the saltiest major ocean basin on Earth. Its surface salinity typically ranges between 33 and 37 parts per thousand.
Why is it saltier than, say, the Pacific?
That high salinity is a really core feature, and it's maintained by a couple of huge global mechanisms. First, down south, you have something called the Agulhas leakage.
Agulhas leakage.
Yeah, it's where enormous rings, or eddies, of very salty water from the Indian Ocean, which is generally warmer and saltier, break off and spill into the South Atlantic around the southern tip of Africa. This constant infusion adds a lot to the Atlantic's overall salt budget.
Okay, that's one source. What's the other?
The other big one we call the atmospheric bridge. This has to do with evaporation and wind patterns. Evaporation rates over the Atlantic, particularly in the subtropical regions, are exceptionally high.
So it's losing fresh water faster.
Exactly. A lot of that evaporated water vapor is then carried eastward by the prevailing winds, crosses Central America, and eventually falls as rain over the Pacific Ocean.
Huh. So the Atlantic effectively exports fresh water to the Pacific through the atmosphere.
That's the concept. It loses fresh water, leaving the remaining Atlantic water saltier. It's a massive planetary-scale salt exchange mechanism, and it's critical for creating the dense water needed to drive deep ocean circulation.
Right, the circulation. Let's talk about how the water actually moves. Surface currents are dominated by gyres, right?
Yes, these huge rotating current systems. Driven by winds and the Coriolis effect, the Earth's rotation, the surface waters in the North Atlantic circulate in a clockwise direction. That's the system dominated by the Gulf Stream.
And in the South Atlantic.
It's the opposite. The South Atlantic gyre circulates counterclockwise.
And this surface circulation, particularly the Gulf Stream system, is famously important for Europe's climate.
Hugely important. The Gulf Stream flows northeastward, eventually becoming the North Atlantic Current, or North Atlantic Drift. It acts like an enormous heat pump. It transports just incredible amounts of heat stored in the water from the tropical regions up towards northern Europe.
And this is why places like the UK or Scandinavia are much warmer than, say, parts of Canada at the same latitude.
Absolutely. This flow significantly moderates the temperatures in the North Atlantic region and across Western Europe. Our sources explicitly state that without this massive oceanic heat transport, temperatures there would plunge dramatically. It's what provides that anomalously mild, temperate climate that defines northwestern Europe.
But that's just the surface. The real global thermostat involves the deep ocean, too, right? The meridional overturning circulation, or MOC.
Exactly. The MOC is the big one, the planetary conveyor belt of ocean circulation. It's driven by density differences, what we call thermohaline circulation. Thermo for heat, haline for salt.
And the key part that happens in the Atlantic is the formation of North Atlantic deep water, or NADW.
NADW formation is the absolute engine of the MOC. It's the critical downwelling part of the conveyor. What happens is warm, very salty Atlantic surface water flows northward. As it reaches the subpolar regions, like the Labrador Sea and the Nordic Seas,
It cools down rapidly.
very rapidly, especially in winter. As the salty water cools, it becomes extremely dense, much denser than the water beneath it.
And dense water sinks.
Right, it sinks. This process of deep convection, especially where the water flows over underwater ridges between Greenland, Iceland, and Scotland, known as the Greenland-Scotland Sill Complex, forces this huge mass of cold, salty water downwards.
And that sinking pulls more warm water north.
Precisely. Once formed, this incredibly dense, cold NADW spreads southward at great depths, filling the deep Atlantic basin and eventually circulating globally. That sinking process is what draws the warm surface water, like the Gulf Stream, northward to replace it. The rate and stability of NADW formation are absolutely fundamental to global heat distribution and maintaining our current climate patterns.
It's mind-boggling to think about this massive, invisible river flowing thousands of meters down. How on earth do scientists actually track it?
Well, this is where science gets quite clever and actually uses some rather unfortunate historical legacies to its advantage. Because NADW is formed from surface water that was recently at the surface, it carries chemical tracers that were introduced into the atmosphere and ocean over the last century or so.
Human-made tracers.
Exactly. Specifically, oceanographers track substances like tritium and certain isotopes of radiocarbon. These were released in significant amounts during the atmospheric nuclear weapons tests, mainly in the 1960s.
So the fallout from nuclear bombs helps map the deep ocean.
In a way, yes. They also track other human-made chemicals like chlorofluorocarbons, or CFCs, which were used as refrigerants and propellants.
How does that work?
By measuring the concentration of these tracers at different depths and locations, scientists can figure out how long it has been since that particular parcel of water was last at the surface. They can essentially determine the age of the deep water
Like
mass.
giving them a timestamp.
Exactly. This allows them to literally trace the path and calculate the speed of the NADW as it flows southward and spreads throughout the deep global ocean. This ability to track the deep flow is absolutely vital for testing and improving the climate models we rely on to predict future change.
Okay, let's shift gears slightly to a really unique feature of the Atlantic, the Sargasso Sea. This isn't a sea defined by coastlines, is it?
No, not at all. The Sargasso Sea is fascinating because it's essentially a sea within an ocean. It's a vast area, maybe 4,000 kilometers wide, in the western part of the North Atlantic, and it's entirely bounded by ocean currents, not land. It's encircled by the Gulf Stream, the North Atlantic Current, the Canary Current, and the North Equatorial Current. These currents form a massive, slowly rotating gyre.
And the water inside this gyre is relatively calm.
Very calm and clear and distinct from the surrounding waters. It's famous, of course, for the floating sargassum seaweed.
Right, the stuff it's named after. What's special about that seaweed?
The sargassum there is incredible. This massive population of seaweed isn't attached to the seabed like most seaweeds. It floats freely and maintains itself entirely through vegetative growth, basically. Bits break off and grow into new plants.
So it just keeps reproducing while floating?
Exactly. And this suggests that this floating ecosystem might have been self-sustaining in the open ocean for millions of years. Some scientists think its ancestors might have been floating around in the ancient Tethys Ocean back in the Tertiary period. It's a truly unique pelagic ecosystem.
And it creates a habitat, right? A floating island almost.
Definitely. It's home to a whole community of specially adapted creatures. The most famous is probably the sargassum fish.
What's that?
It's a type of anglerfish, but it's incredibly camouflaged. It has these weird algae-like flaps and appendages all over its body that make it blend in perfectly with the floating sargassum mats. It just hangs there motionless, ambushing smaller prey. A fantastic example of adaptation.
But the Sargasso Sea holds perhaps an even bigger biological mystery involving eels.
Ah, yes, the eels. This is one of the great stories of animal migration. The Sargasso Sea is the only known spawning ground for both the European eel and the American eel.
Both species spawn in the same area.
Apparently so, in the southern part of the Sargasso Sea. And the journey, especially for the European eel, is just staggering.
How far do they travel?
Adult European eels migrate from freshwater rivers all across Europe. We're talking over 5,000 kilometers, sometimes more. They swim all the way to the Sargasso Sea, spawn deep in the water column, and then presumably they die.
And the babies have to get back.
Yes. Their larvae, which are tiny, transparent, and leaf-shaped, called leptocephali, are then carried passively by the Gulf Stream and North Atlantic currents back towards the coasts of Europe, a journey that can take 1 to 3 years.
That's incredible. How did the adults possibly navigate that huge distance to find this specific spot in the middle of the ocean? And how did the larvae end up back in the right continental river systems?
The navigation is the really big question, the holy grail of eel research. We know the larval drift is largely passive, driven by currents, but for the adults getting there, and maybe even the young eels or glass eels, orienting themselves as they approach the coast. Recent research using tagging and tracking strongly suggests they use the Earth's magnetic field.
Like an internal compass.
Exactly. It seems they can sense the planet's magnetic field lines and potentially use them to navigate across these vast, seemingly featureless expanses of ocean. It turns the Atlantic from just a big body of water into this complex, magnetically mapped highway for migration. Still lots to learn, but it's fascinating stuff.
It really is. Okay, let's pivot now from deep time and biology to human history interacting with the Atlantic. We know the Norse crossed it first, reaching North America around 1000 AD.
Right, the Vikings got there first. Settlements like L'Anse aux Meadows and Newfoundland are proof. But their impact wasn't sustained globally.
So the real turning point was Christopher Columbus in 1492.
Absolutely. Columbus's voyages, funded by Spain, were the catalyst. They ushered in the age of exploration, spurred massive advancements in shipbuilding and navigation, and of course led directly to the European colonization of the Americas.
And that connection instantly made the Atlantic the central hub of global interaction.
It became the absolute crossroads with massive consequences, both positive and negative. It kicked off the Columbian Exchange, that huge transfer of plants, animals, technologies, cultures, ideas.
And devastatingly diseases.
And diseases, yes, between the eastern and western hemispheres. It reshaped the ecology and societies of both sides of the ocean forever.
And central to the Atlantic's human history for centuries was the horrific transatlantic slave trade.
Tragically, yes. From roughly the 16th century through to the 19th century, the Atlantic was the main route for the forced transportation of enslaved Africans. The estimates vary, but our sources cite around 9.5 million people forcibly shipped to the New World.
Primarily for labor.
Primarily for brutal forced labor on plantations, especially sugar, tobacco, and cotton plantations in the Caribbean, Brazil, and the southern colonies of North America. This exploitation was a foundational, albeit horrific, element driving the economic growth of the Atlantic-facing European powers.
And that economic impact was really concentrated on those countries with direct Atlantic access, wasn't it? Like Britain, France, Spain, Portugal, the Netherlands.
Disproportionately so. Transatlantic trade involving slaves, raw materials from the colonies, and manufactured goods from Europe became absolutely crucial for their sustained economic growth and wealth accumulation.
Is there a way to quantify that advantage?
Yes, the sources provide some striking data. Look at urbanization rates, for example. Between 1500 and 1850, the percentage of the population living in cities in those Atlantic-facing European countries jumped from about 10% to nearly 24.5%.
And elsewhere in Europe.
In the rest of Europe, urbanization grew much more slowly over the same period, from about 11.4% to only 17%.
It's a big difference.
It is, and GDP figures show a similar pattern. The GDP in those Atlantic countries roughly doubled during that period, while in the rest of Europe, it only grew by about 30%. By the late 1600s, the sheer volume of trade crossing the Atlantic had actually surpassed the volume of trade in the historically dominant Mediterranean Sea.
Wow. And a significant part of that Atlantic wealth, at least initially, came from fishing, right? Those continental shelves?
Yes. The relatively shallow waters over the continental shelves bordering the Atlantic are incredibly productive ecosystems. Places like the Grand Banks off Newfoundland, the Georges Bank off New England, the North Sea's Dogger Bank, the Falkland Banks down south. These areas host some of the richest fishing grounds in the entire world, thanks to nutrient upwelling and ideal conditions for fish stocks like cod, haddock, herring, and others.
But that richness led to overexploitation, most famously with the collapse of the Northwest Atlantic cod fishery.
That's the textbook cautionary tale, isn't it? It perfectly illustrates what happens when fishing capacity outstrips the resource and regulation fails to keep pace. Fishing happened there for centuries by indigenous peoples and later Europeans, but the real crisis ramped up dramatically after World War II.
What changed?
Technology and scale. Large, powerful, distant water fishing fleets from Europe and Asia started arriving. These were factory trawlers with onboard processing, powerful engines, and advanced fish-finding sonar. They had the capacity to catch fish on an industrial scale far faster than the cod stocks could possibly reproduce.
And because much of this was in international waters, regulation was difficult.
Exactly. Overfishing was being documented by scientists as early as the 1960s, but getting effective international agreements and enforcement in place lagged way behind the fishing effort. This relentless pressure led directly to the catastrophic collapse in the early 1990s.
Forcing fishing bans.
Yes, complete moratoria had to be imposed, particularly in Canadian waters, devastating coastal communities. The numbers are stark. Total fish landings in the Northwest Atlantic crashed from a peak of around 4.2 million tons in the early 1970s down to just 1.9 million tons by 2013.
Have the stocks recovered?
Some have shown signs of slow recovery, but many, including cod in some areas, remain severely depleted. Even today, sources indicate that about 31% of the assessed fish stocks in that Northwest Atlantic region are still categorized as being overfished, a long-lasting impact.
Moving to other modern environmental challenges, pollution is obviously a major issue for the Atlantic.
It is, and a lot of marine pollution originates on land. Rivers act like pipelines, carrying runoff from farms, fertilizers, pesticides, and industrial discharges, plus urban wastewater directly into coastal waters.
Creating problems like hypoxia.
Yes, hypoxia oxygen depletion. The excess nutrients, especially nitrogen and phosphorus from agriculture, cause huge algal blooms. When these algae die and decompose, the process consumes oxygen in the water, leading to dead zones where fish and other marine life simply can't survive. The Gulf of Mexico has a particularly notorious large dead zone linked to Mississippi River runoff.
And then there's the physical pollution, the plastics and debris.
Right. We can't ignore the sheer volume of trash entering the ocean. Plastic is particularly problematic because it doesn't readily biodegrade. The ocean currents, those same gyres we discussed, tend to concentrate floating debris.
Leading to things like the North Atlantic garbage patch.
Exactly. It's not a solid island of trash, but rather a huge area, hundreds of kilometers across, within the Sargasso Sea Gyre, where the concentration of microplastics and other floating debris is significantly higher than elsewhere. It shows how the ocean's own circulation patterns inadvertently trap our waste.
Finally, let's talk climate change connections. The Atlantic seems to be on the front line there, too.
Very much so. There's strong evidence, for instance, that North Atlantic hurricane activity, both frequency and intensity, has increased over the past few decades.
And that's linked to warmer water.
Directly correlated with rising sea surface temperatures, or SSTs. And careful statistical analysis accounting for natural cycles strongly suggests that this trend is primarily driven by anthropogenic, human-caused climate change, not just natural variability.
But maybe the most critical climate finding relates back to that deep ocean circulation, the AMOC.
Yes, the Atlantic meridional overturning circulation. The health of this system is a major focus of climate science, and the recent findings are, well, they're concerning. While concerns about a slowdown were raised back in 2005, more recent studies, including some published in 2024 cited in our sources, indicate a continued significant weakening. The estimate is around a 12% slowdown over just the last 2 decades.
12% in 20 years. That sounds substantial. What's causing it?
The leading hypothesis is the increased meltwater flowing into the North Atlantic, especially from the Greenland ice sheet. This influx of fresh water makes the surface water less salty and therefore less dense.
Making it harder for it to sink.
Exactly. It weakens that engine of deep water formation we talked about, slowing down the entire conveyor belt circulation.
What are the potential consequences if the AMOC continues to weaken or, worst case, collapses?
The implications are massive and complex. Regionally, a significantly weaker AMOC would mean less heat transported northward. This could lead to paradoxical localized cooling, particularly in northwestern Europe. Even as the rest of the planet warms, it could also shift rainfall patterns.
And globally?
Globally, the oceans, especially the deep layers, are currently absorbing a huge amount of excess heat trapped by greenhouse gases. This provides a crucial buffer, a time lag for the full impact of climate change. But that absorbed heat causes the water itself to expand thermal expansion.
So sea levels rise not just from melting ice, but because the water itself is getting bigger.
Precisely. And if the AMOC slows, it affects how and where that heat is stored. Projecting forward, the long-term effects are stark. Even without a full collapse, the combination of continued ocean warming, thermal expansion, and meltwater from ice sheets like Greenland and Antarctica points towards significant future sea level rise.
How much were we talking?
Over the timescale of centuries to a millennium, the committed sea level rise just from thermal expansion and the melting already underway is projected to be several meters. Our sources mention figures in the range of 3 to 6 meters eventually. The Atlantic's capacity to absorb heat is fundamentally linked to the long-term fate of global coastlines.
Wow. So this deep dive has taken us from ancient myths about Atlas all the way to the physics of thermohaline circulation and the future of coastal cities. We've covered the colossal volcanic events that birthed the ocean, the incredible journeys of eels, the rise and fall of fisheries. It's a huge story.
It really is. And what's so compelling is that while we've charted this immense history, the Atlantic story is definitely not over. Geologically speaking, it's still an opening ocean basin, right? The mid-Atlantic ridge is actively creating new seafloor every day.
So it's still growing.
It is. But the processes that govern the life cycle of oceans, often called the Wilson cycle, suggest that even as it expands, the seeds of its eventual closure are already being sown.
We've seen how oceans open through rifting, but they eventually have to close again as continents collide, right? What's the evidence that the Atlantic might be heading towards that eventual end, even if it's millions of years away?
The first subtle clues lie in the initiation of subduction. That's the process where one tectonic plate starts to slide beneath another, which is how ocean basins are ultimately consumed.
And we're seeing signs of that starting around the Atlantic.
Yes, in specific zones. Geologists are closely monitoring what they call an embryonic subduction margin developing west of Gibraltar. The Gibraltar Arc, a curved mountain belt, seems to be actively migrating westward into the Atlantic, potentially indicating the very early stages of the African plate starting to slide under the Eurasian plate there. Similarly, complex plate movements down south in the Scotia Arc region near Antarctica between South America and the Antarctic Peninsula also suggest areas where the Atlantic oceanic crust is beginning to be consumed.
So these are the first incredibly slow steps towards contraction.
Exactly. They're the faint initial signals that the long process of closing the Atlantic might have already begun in certain areas, even while the MAR continues to churn out new crust in the middle.
That's an incredible paradox. The Atlantic is simultaneously being created and, in a way, starting to be destroyed, building itself up and laying the groundwork for its own demise.
It captures the immense timescale and cyclical nature of geology perfectly.
So let's leave our listeners with this. We see the Mid-Atlantic Ridge making new ocean floor daily, widening the pond. But other immense geological forces are already hinting at its ultimate closure, countless millennia from now, when those continents finally do reconverge, crushing the Atlantic basin out of existence. What name will future geologists, maybe not even human ones, give to the next supercontinent that forms when the pond is finally gone?